Okay. Yesterday, we spent a lot of time discussing the different impacts of the system layers on the performance equation, right? Instruction count, CPI, and clock frequency. And hopefully, this gives you a very good idea of how to make trade-offs, as we will see later on in the architecture discussion. But these performance lectures that we have finished, like yesterday and last week, Friday, very, very key to the rest of the course. My suggestion is make sure you understand performance very well. Also in the tutorial yesterday, I solved some problems with you. Any discussion we're going to have in this course is related to how do we improve performance, right? So we're going to say, we discuss pipeline as a concept that enables us to improve performance. What is the impact on CPI and IBC, instruction latency and throughput? Then we're going to discuss caches. We're going to discuss different trade-offs on how caches really improve performance. And every single architecture concept, whether it's pipelining, out-of-order execution, caching, memories, all of these things, we come back to their impact on performance and what are the trade-offs. To make sure you understand this lecture very well and know how to solve problems, and it comes to you naturally, because this is how architects make decisions, right? I come up with an idea again, then I need to assess, does it make sense? Does it make sense? What term in the performance equation is going to help and what term is going to impact, right? And we're going to have a lot of these discussions for every topic we discuss. So you have to be aware of this. It just has to come naturally. You don't need to think about it. Good. So as an introduction to the concepts we're going to discuss, I found myself last year that we have to go through 2 lectures that are not, in fact, a key topic in our architecture course, right? They are usually the topic in our computer organization course. And part of these lectures are the ISA discussion. ISA is usually a topic that is assumed to be known before you come to an architecture course, right? From previous courses, from organization courses. But because we don't teach an organization course, I know that you're not fully aware of this, right? So we're going to spend a couple of lectures going to ISA. Without understanding the ISA, we said ISA is the contract between the hardware and software. So again, as an architect in the hardware, you are implementing the ISA, right? So that's basically the document you open, look into instructions, and build your circuits based on this one, right? Based on the series of bits of the opcodes, of the registered operands, and what operations you need to support, what flags you need to support. So without understanding the ISA, you will not be able to build a computer, right? Like a computing machine, a processor circuit, data path and control path. Good. So this is why we're going to go through like the ISA in some sort of a detail. Good. I do understand also, I guess, from my earlier discussions with Professor Bowman, that maybe in the end of the digital design course, 2DI, you might have wrote some assembly code. Is that a true statement? No, because she did this in few years and few other years not. So how many of you wrote or saw an assembly code before? Can you raise your hand? Well, that's in fact quite a good number, right? I expected way less number. So at least you're aware of what assembly. As we said yesterday, we're going to pick up an example of an ISA that is easy to discuss in the lecture, right? Which is a RISC type ISA, which is the MIPS, right? Instruction set. It doesn't mean by any means that whatever we're going to discuss does not apply to other ISAs, but you have to pick an example to basically have a tangible feeling out of it, right? But all the concepts apply to any other ISA, and more likely to apply to RISC instruction set more than like the CISC ones. So in the MIPS R3000 ISA, we have some instruction categories. And then why do we define categories? Because later on, we need to define the fields of the instruction. We have what we call computational instructions and then load store instructions. Remember, we said in a RISC instruction set, you are only access the memory through load store operation, right? Any other instruction is not able to access the memory. This is why it's important to differentiate load store from anything else. Good. And this is common theme for any RISC instruction set. Open the ARM instruction set, the RISC-V instruction set. You will find that the load store instructions or set of instructions are separate from the arithmetic and logic and any type like control flow instructions. because these are the only ones accessing the memory. And then we have the control ones, which are jump and branch. And then we can have floating point. In this type of machine, it was a coprocessor. I guess I might have mentioned to you this in maybe like this week, not yesterday, I believe, the last week, that at early days of computer architecture, for example, floating point wasn't natively supported in architecture, right? It was implemented as a coprocessor. So the instruction set defines it, but the hardware does not implement it. It goes to software routines to implement it. So in this MIPS R3000, it's a very old machine. It was a coprocessor. In most current existing processors, floating point is natively implemented in the pipeline, right? So it's part of the function units we implement in your processor. You don't have to think about a coprocessor or anything. Then some memory management instructions that we don't have to worry about them too much. And then there is some special instructions you need to add to handle your pipeline precise state in a shape that we're going to visit way later in the course. So these two especially, you don't have to worry too much about them when you talk about the IC in today's lecture. All these instruction categories, they are being combined in the MIPS instruction set in 3 instruction formats, right? What we call the R format, the I format, and the J format. And the naming, really, this kind of format has a meaning. R means you are mainly operating on register, right? So there is a register operand there, right? And this also includes the load store ones, and you see. This is the I format. This is because some of the arithmetic instructions operate in immediate value, right? If you write something like add R1, something like this, add R1, and then 3. This is an instruction that is needed to translate something from the high-level programming as like this, x equal x plus 3, right? So you want to add the register to 3 and then, well, update it with this. So you're incrementing by 3, right? So this is an instruction that has one operand input, right? This is an input operand. It has one output operand, but then it has an immediate value, right? That's why we need a special type of instruction that has a field for immediate value. This is different than saying add R1, and R2, where both are 2 operands. Why it's different from the ISA perspective is because if you have 32 registers, how many bits you need to identify a register in this register file? 5 bits, right? 32, you need 5 bits. But if you are operating on, which means these operands like the RD and then the RS, and most of these operands are basically 5 bits. But if I'm supporting immediate value, how many bits do I need? Theoretically, like aside from how MIPS implemented, like if you need to support something like this, how many bits do you need for the immediate value? The maximum you can support, right? So if you have, this is like a 32-bit machine and your integers are 32 and you're adding integers, then you need 32 bits, right? You see the problem? That's a big problem because all our instruction bits are 32. I cannot really dedicate 32 bits for an immediate value, right? So you need to support as many bits as you can. So this field has to be a big field, but at the end of the day, it has a limit. This limit puts a constraint on how big is the immediate value that you can support, right? So for example, in this instruction set, we dedicate 16 bits for the immediate value, which means I can add up to a maximum for 16 minus 1. Any immediate value that is larger than this, I cannot support using an immediate instruction. What can I do? Is there something that comes to your mind to solve that problem? Yeah. Store the value in a register and then use that register. Well, a good point. But to store that value in a register, you need to read it, put it in the register. It's sending the 32 bits, right? Yeah. Good. But what are these? How can I break? A good point. Yeah. So that's really the philosophy of how this side of instruction can support larger immediate value. You use the low high bits and then you break it down into different numbers, then you combine. Good. So if I combine these two answers together, which is in fact what you said is a true step there, but then you need to store it in 2 directions. Like you need to take the low first, which are basically 16 bits, put it in one register, maybe the low of the register, then take the second 16 bits, put this in the high of the register, and then use the registers to add, for example, right? We're going to discuss this later on, but just to have a sense of how ISA definition limits your implementation, limits the capabilities the machine that can have, right? This is because it's a contract. Once you 32-bit immediate values, add them direct to a register because the ISA does not support that. Right? Then finally, there is a very special type of instruction that will come a lot in this article because there's a lot of headaches later on also in the lines or branches, right? The jumps. Things we discussed in the first lecture about you have a for loop, we have an if condition, we have a function call. So you need to jump your address. So these are the jump or branch instructions, and they have the J format. The J format simply has an and then you have the jump condition. To face the similar problem, ideally, what would be your jump address width? How many bits I need for the address to jump? If this is a 32-bit machine, you need 32 bits for your program counter, right? To jump to the new instruction. I cannot put 32 bits in that instruction count because I send you bits without code. You have a limited number of bits for your jump address. You make it as big as you can. This instruction is 24 bits. You leave the rest of the bits or just 8 bits without code, but you use 24 bits for the jump address. What is the limitation of this? Can you think of a limitation of this when you execute a certain code? If I only have 24 bits for my jump address, if I write a for loop, well, maybe not a for loop. So, or yeah, a for loop that has a very large body, that's okay as well. But at the end of the day, this is going to be at the end of this for in the assembly, you're going to have a conditional branch not equal, for example, right? And then this branch, where it will go back at the beginning of the loop, right? So you keep doing in the looping of the assembly until you simply break the condition and you exit the loop. Now, if I'm telling you, well, this arrow that I have is your jump address, right? So this is your jump target. If I'm telling you that this jump target can only be 24 bits, what is the limitation of this? What constraint puts on me? This created assembly.
Can't put 24 bits
away from you. Yeah. So the distance of your jump, because in an assembly, the jump has an offset, right? You jump from the current location. So you have the program counter of the current instruction, and you jump relative to that instruction, either before or after, right? So this relative distance between instructions for the jump cannot be more than 24 bit, right? So you put a limit on how far you can jump in your code, right? Sense? Good. Then another topic that we will need when we discuss ISA is simply the unsigned binary registry. So some instructions, especially for immediate values, is signed value, not signed value. This is a pretty much review out of 2DI. I'm not going to spend a lot of time on, but the key takeaway here, if I say I have a 32-bit integer, then what values do I support for that integer? Well, you have 2 to the power 32 minus 1 combinations, right? But if you support signed numbers, half of these numbers will be negative, half of them will be positive, right? So in reality, you have 2 to the power 31, half of this in the negative side, and then you have 2 to the power 31 minus 1 in the positive side, and in between you have the 0, right? So half of your width of the bits will go to the negative and half will go to the positive. Now, as for example, a high-level programmer in 2SH or 2SI, how does this impact me? One way to think about it, if you know your variable will always be positive, you are deploying a counter, for example, and you are defining this as an integer, and you know that your counter will basically go for very high values. How should you define it to make the best use of the bits of the counter? Yeah, unsigned. Thank you. So the idea is, if I define my integer to be unsigned int or uint in C, this makes me take the full width of the 32, go from 0 to 2 to the power 32 minus 1, right? So this full half now came to all to be positive, right? So I used all of the bits. If I'm using it as to be unsigned, the biggest number I have is only 16 bits here, or 51 bits, but it's half of the number, right? You see what I mean? Like, to have a sense of this, if you only have 8 bits, and those are signed, then in reality, you can only support from -7 to 7, right? Why? Because you have 1 bit for the sign. You are left with 3 bits. The maximum of 111 is 7, right? So you have -7 to 7. But if you, did I say 8 bits? Sorry, I should say 4 bits, right? Now, if I have the same 4 bits and I'm using them for an unsigned number, what are the values I'm supporting? Is from 0 to 16, right? Well, which is basically 16 minus 1, which is 15, right? So you took the full number width. So you went from 7 to 15 as your counting value, right? So you have to be very careful, especially when it was in 4DS. You have a very limited resource device, like a microcontroller or something, or an IoT device, where really memory is very precious. You have to pay attention to the types of the variables they use and what is the best type you can have to identify them, right? Good. But other than this, I will leave this for you to review. I'm hoping by 4th year, binary representation comes very natural to you, right? Great. Now, another thing that comes in also from 2DI is the ASCII representation, right? So simply you have, other than numbers, you have letters, you have special characters in your keyboard, and you need to encode them into your binary representation. How do we encode them? You must have a standard way, otherwise you are not able to build machines. This standard way is the ASCII representation. Right? What does ASCII really give you? Well, simply tells you for every character that has an ASCII number, this ASCII number is going to be translated into a unique binary value. Good. Something I assume you have seen before, but it's also important to revise. Given that we get away from this revision of 2DI, we go back to our instructions. So we start by the arithmetic ones. Arithmetic instructions, simply something like add or sub or multiply or divide. It's written like this. You have 2 source operands, and then you have a destination. So what you want to do is you add S1 plus S2 and put the result in T0. Similarly, for the subtraction, while I'm subtracting S1 minus S2, and then I'm putting the result in T0. So in general, the format is I have a source, another source, there is an operation in between them that is defined by the opcode of the instruction, and I have a destination to put back the result, right? This basically defines source 1, source 2, and the destination, and the operation is defined by the instruction itself. Something that the ISA also defines as part of the contract. When I'm embedding this hardware, I need to know if I receive those bits from the memory to my decode unit, I should be able to extract the feeds. I should be able to extract this is the opcode of the instruction and it means an add. I should be able to extract that this is the first operand, the second operand, and I should put the result in this result operand, right? To be able to extract this, you must have well-defined locations for your fields. Otherwise, the hardware, well, the compiler will create the assembly by putting, for example, source 1 in a certain location, while the hardware will envision that the location is somewhere else, and it will bring the wrong number. So you break the contract. This is why the ISA, it defines how the instruction is created, but also where you should find different fields. If I go back here, the types we define. You will find that part of the definition is where you should find every field, right? Source 1, source 2, and destination, right? And even if you have an immediate value, where you should expect it. If you have a jump target address, what you should expect. Okay? So those fields are well defined in the ISA as part of the instruction. And if we are talking about an R-type instruction where you are operating in registers, all of these registers are stored in a register file, and they have a certain address, right? In the MIPS, you have 32 registers, general purpose registers, which means you need 5 bits for the address. Good. Here there are some register conventions for the MIPS ISA, but in reality, you don't have to know this by heart, right? Like it's just an example. Most ISAs define some convention such that the compilers creating the assembly follow that convention. Anyone looking into the assembly, they are able to relate to what this register is doing. For example, if I'm doing this 0, well, I'm referring to a register that has a constant 0 value, right? If I'm referring to a global pointer, then it's GB, stack pointer SP, frame pointer is FP. And in reality, all these registers more or less use the same convention even across ISA, right? If you look into an x86 assembly code, you will find that the stack pointer is called SP as well. Okay? But again, the convention really is not something that you should focus a lot on. Now, relating this to the hardware, we said the arithmetic instructions operate on registers. Registers are stored in a register file. In 3DQ, did you come across building register files? Like just a big chunk of memory that basically it work as very fast memory to access, right? The idea is that in this MIPS machine or in even modern machine, those registers are tightly coupled to the processing pipeline. They are close to the ALU, which means this is the fastest memory you can access, right? You always prefer to access the register file than to go to the memory to access, right? Because it's just a single cycle access time. In the MIPS machine, we have 32 locations, and this register file has some ports. It has a source 1 address port, source 2 address port, destination address port, and then, well, if there is a data that I'm writing, I'm writing this data, well, write enable, and then simply other 2 data ports to read the data, and that's it. So now, why I'm building it that way? Why I'm building the register file to have 2 read ports and 1 write port? What do you think? From the ISA we just discussed, why do I choose to have 2 write ports and 1 write? Why not, for example, 2 write ports and 2 read ports, or 1 and 1? Yeah, you see. Yeah, exactly. At maximum, those instructions would require 2 read operands and 1 destination output. Some instructions will have only 1 read operand, but at maximum you need 2. So if you were to build a register file with only 1 read port, what would be the cost of this? What is the trade-off you are making here? First of all, what do you gain if you build only 1 read port? So compare a register file with 2 read ports with a register file with 1 read port. Why 1 read port might be beneficial? Yeah. That's true. That's a good idea. But usually, if you have 2 read ports, you also separate the address into 2. So a port really means both for data and address, right? But yeah, you complicate your life a little bit. But the point of faster is not completely true, because a port has a high cost that is known. Like anyone that is working, for example, if you had a co-op on a digital design company or somebody that goes through silicon manufacturing, ports are the most expensive resource in terms of area, right? You want to minimize number of ports at any expense. Good. So having higher number of ports means definitely higher area. Why area is problematic? It's higher costs. You take more area in your chip, you have to pay more. Good. Then if it's a higher cost, why do I choose to do 2? Because if you have chosen to do 1, then what is the cost of this? Can we implement this instruction set using only 1 read port? That's what, can we or we cannot? Like if we have instructions that would need 2 read operands, something like add, just to visualize it in front of you. And there is R1, R2, R3. So I need to read 2 registers and then update a 3rd one. If I only have a register file with 1 read port, how do I do this operation? Take 2 cycles, right? You read the first one, wait, because the register file, 1 port allows you to read 1 register at a time. So you have to do it over 2 times. So you increase the number of cycles required for those instructions, right? Now, by choosing to have 2 read ports, you traded area for performance, right? You said, I'm willing to pay 1 extra read port to make sure that I can finish these instructions in 1 cycle. Good. So this is an example of you are making a trade-off that you are aware of, right? And this takes us again to Amdahl's law. Amdahl's law, or even the general rule of computer architecture. You make the common case fast. Why did I make that choice? Because most instructions have 2 read ports, right? So most instructions will benefit from an additional, most instructions have 2 operands. So the most instructions will benefit from 2 read ports. So it's a wise decision to make, right? You trade this area for, again, performance. That is very common. Good. Questions? yeah, we said the registers are very fast and you are willing to really use them to access them, but they're very limited resource. There's only 32 of them. Now, going to our add example, adding S1, S2, and then put the result T3. How do I architect my fields of the add instruction to reflect this add? First of all, some of the fields will represent that this is an add operation, right? Because of that type, which is our type, it can be an add, it can be a mul, it can be a sub, it can be anything else, shift, right? So you need some fields to represent this an add operation. This is the output field and the function, the website instruction. Then you need something that holds in the address of the first operand. And we said this field is 5 chess because you have 32-bit registers. Right? You need to hold the address of the register. Then you need also the same thing for the second operand. And then finally, you have something for the destination, which is RD, right? So the ISA is telling you, I find my opcode here and here, and you find your sources here. Why this is important? Because if I'm building my decode unit, I'm going to bring this instruction from the memory, take the opcode field and the function field, do the decode, discover it's an add. If this is an add, I know that I need 2 registers. So I take these locations of operand 1 and operand 2, go to the register file, read them, do the add operation in the ALU, and then write the results in the field that is indexed by RG. Good. So in the MIPS, the op is 6 bits and the function is 6 bits. And then that means you use 12 bits to really determine different instructions out of the arithmetic instruction format. And then you have simply, 35 bits for the source destination. The shift amount, this last field that we use for that. This is done to basically support shift and stuff. Shift, left shift, right, arithmetic shift, and logic shift, right? Because sometimes the shift instruction is still an arithmetic type instruction, but you need to shift with a certain amount, which is an immediate value, right? So this is your shift amount. Okay, so this is for arithmetic type. Then we said for memory, I only have 2 types of instructions, either loading from the memory or storing from the memory. An example here is the LW, which is a load word instruction. So something that I'm a little bit surprised about, but I found a lot on teaching that course in different places, that people are confused between loads and stores. I don't know why. For loading, am I writing to the memory or reading from the memory? What do you think? When I say memory load, am I writing to the memory or reading from it? Reading from it, right? So loading is in fact loading from the memory, right? So loading means you read from the memory and write to a register. Store means you take a register and write it to the memory. Good. The load is a memory read request. A store is a memory write request. That's very important on understanding how the architecture really works for the load and store. Good. And I don't know why this creates confusion. Like sometimes people think of a store as I'm really reading the memory and writing it in a register, right? So when we say this load, and this is basically how do I put the store? So let's visualize it first before we stop using this thing. So for the load, what I'm really doing, so I have my memory here, and then I have a register that is S2. Then I have a register that is T0. What do I want to do? Or what does this instruction tells me to do? Take S2 value, add it to 24. This gives you an address that you go to your memory, bring some data, XXX, put it into T0. So there are 3 steps here. First of all, read S2 and calculate the offset. So you add it. So there is an add instruction to calculate the address. Because there is an offset, which is written like this. So add both. This gives you a final address that you go to the memory with this address, bring data, and write it to your destination register. Good. So how do I include this in the ISA? Simply, you also have operands. You leave bits for the offset, which is this offset. It's again 16-bit only. And then you have the source operand, which is the one that you are used to calculate the address. And then you have the destination where you write your loaded data. Okay. Yeah, so that's I guess what is being visualized here. You add S2 to 24, you go to the memory, bring some data, and then you load it to, well, this is, you do the addition operation, you go with this address, and then you simply get the value from here, put it into T0. Something to understand, and I hope this is already mentioned in 2DI, is that you always assume your memory, this is how every computer is being built, your memory is byte addressable. Did you hear that term before? Byte addressable memory? In 2DX as well, like, because you dealt with in the project, you dealt with memory in your MCU, right? So memories are byte addressable. What does it mean? It means that any address you have to the memory is going to bring you back. It's pointing to a single byte in the memory. Okay, and we mentioned this even in 2SH when we talk about how integer is being stored in the memory, because integer is 4 bytes. Basically, the address of the pointer will be pointing to the first byte of these 4 bytes, and you read the 4 subsequent bytes, right? There's something related to this discussion, and these are often encoding. So now I have one address, and I go to the memory to read more than 1 byte, an integer, for example, value, because you are loading to a register, so you are loading 32 bits, right? If you are loading a word, you need to read 4 bytes. Which 4 bytes do I read? Is my address pointing to the first byte or to the last byte, right? This is basically the differentiation of a big Indian and little Indian machine. So simply, if you have a little Indian machine, that means your first byte you bring from the memory, which is the address is pointing to, is the least significant byte of the word. Okay, so little Indian is, I guess, the more conventional way of thinking. I have an address, I get the first byte, it's the least significant byte. Subsequent one is the one after, the one after, the one after, right? In a big Indian machine, in reality, you bring the first byte, you put it at the most significant. Good. Well, it's also, in fact, compatibility. Like right now, ARM, they have cores in the same SoC that some of them are little Indian and some of them are big Indian, right? And in reality, it's something that I don't know why done that. It's very confusing. To be honest, last year we were also working in a very big project in RISC-V, and it's one of the biggest projects in RISC-V in the world. That like there are some cores that are very well known to be RISC-V used, and there was a bug that like took 3 months to discover, and at the end of the day, we discovered is the core is little Indian, but the actual memory is assuming big Indian, and there is a mess somewhere in between that they forgot to translate, right? So it's a bug related exactly to the slide, and it takes a lot of time to figure out because you will not. It's not easy to debug hardware to realize that somewhere you missed the order where you should be reading this first byte, but at the end it's second byte, right? And this comes a lot in industry because of integration. Most likely, if you are building your machine from scratch, you will say, okay, why I should be doing this, right? From the beginning, I assume little Indian or big Indian. So you might think it doesn't make any sense where I mix these, right? But in reality, 30% of IBs in any SoC currently, whether it's in your mobile phone, tablet, iPad, it doesn't really matter. At least 30% are third-party IBs. So you have to go and purchase an IB from somewhere. Now there's an IB that best fits your needs, but it happens to be big Indian. Your phone machine is little Indian. Your choice to make is, should I really bother and buy it because it's very costly or very cost efficient and it fits my needs, and then I build a shim or a translator somewhere, or I should look for another IB or build it from scratch. Most of the time you say, it's already ready, verifiable, good cost, I buy it, and then I build the translation link, right? And you find most SoCs right now building a lot of translations everywhere, right? It's a practical consideration where modern SoCs are heterogeneous and they have different sort of Indianness, big Indian and little Indian. Okay? So it's important to understand, well, what machine is which and what are reading from the memory. And again, this is very especially important for when you write embedded code, because in embedded, you are very close to the low level. You are particularly interested in 1 byte of the data, right? Of course, if you are writing Python, very high level algorithms, you don't care about what's happening here, right? But at least you need to understand something beneath, under the hood is happening that might cause some inefficiencies in your code. Okay. So we talked about loading and storing binary, what bits really I need to write. I need to show you a visualization of how the store really works. So maybe we should visualize for the same example we have here. If I have a store operation, what would I do instead? So if I have a store, go back to this example here. If I have this store, how do I interpret this? It means, again, this is used to calculate the address, but then you take that value and you write it to the memory. So in reality, these two registers in your store operation are source registers. You are not writing in any register in a store operation, right? You're writing to the memory. What you would do is you take S3, add 8 into it, you get your address, go to the memory, to a particular address, then you take T0 and write it here. Right? Like whatever value was in T0, you write it inside the memory. This is how the store will work. Good. When we go in building our control path and data path, we will see how this is important to understand. For example, in a store, you don't need to turn on the write enable of the register file at all. There is no write enable in the register file because I'm not writing to the register file. But I need to read twice from the register file. One to get the address, and one to read the data that I need to write to the memory. The other hand, for a load operation, how many writes and reads I do for the register file? You do only one read to get the address, and then you go to the memory. Once you bring your data, you enable the write enable of the register file to write to the destination. Good. This will come, but I'm just trying to relate to you why this is important to discuss what operations exactly happen for every instruction. Good. So the third type of instruction, so we discussed arithmetic instructions, load, store, which are memory operations, and then finally the control flow operations, the branches, right? Branches and jumps. So here there are two examples of branches. Like one is the branch not equal, the second one is branch equal. They differ only in the condition. What you do is you simply have a label, which is basically an offset, an address that you go to an immediate value. And then here you say you jump to this label, to this address, only if in the first one, if S0 and S1 are not equal, right? So if S0 and S1 are not equal, you jump to label 1. If this is a branch equal instruction, BEQ, it's the other way around. If S0 is equal to S1, you jump to label 1. Good? And here it shows you an example of how this is being used to translate an if condition in C, for example. You say if I equal to J, you do this operation. How do I translate this? Well, this is I can really do it using like a BNE or BEQ, right? In reality, both can be used for this example. But in our example here, in reality, if they are not equal, I'm not executing this one, right? So which means execute the second instruction. So just write a complete C code like this: H equal I plus J. But then, if this is not true, I continue doing anything else, right? And this is going to be my label instruction. So how to interpret this? If these two are equal, execute this first. If they are not equal, jump directly to this. So I want to jump if they are not equal. This is why I'm having a BNE instruction here. And then assuming I and J are loaded in S0 and S1, if they are not equal, jump to label 1. And label 1 will have basically this instruction. If they are equal, I just get the next instruction. I don't jump, which means I'm going to do this addition. Questions? Do you understand how, like, conditions, for example, if conditions are translated into branches in assembly? Good. Okay. How do I specify the destination address in this 16-bit offset? Because this label is going to be translated into a 16-bit offset. First of all, I'm jumping from the current instruction, right? This instruction has a certain address, which is stored in the program count, right? Now, to jump to somewhere else, you are adding the offset to the program count, right? So you say, from the current instruction, relative to it, jump to this location. So you are going to read the program counter of the current instruction, add the offset into it, and then jump to this new instruction. Okay. Yeah, so that's exactly what is being said here. Use the program counter because it's relative. If I'm not jumping, what is going to happen? So here, in this example, if the condition is not true, what is going to happen? I'm going to execute the subsequent instruction. What is the address of the subsequent instruction? If the address of this one is BC, what is the address of this one? Do you think? If B and E has an address BC, what will be the address of the add instruction? BC plus 4, right? Why 4? Because our instructions are 32 bits, 4 bytes, right? So every instruction is consuming 4 bytes in the memory. And we said our memory is byte addressable. So every single address points to a single byte. So if the branch, if you look into your memory and the branch is consuming these 4 bytes and the address here is BC, the next one will start here, which is basically BC plus 4. Good. So if you're not executing your branch, you simply increase your program counter by 4 during the fetch stage that we discussed in the first lecture, right? Now, how do I build this circuitry for the fetch to jump to the branch? And again, this is something that I hope you put in your mind, and we're going to revisit when we talk about a complete pipeline. But now, what is being problematic about a branch? If we don't have branches at all, every single instruction has a known address, right? I start from address whatever, like the first line in the main, let's say 0. Every subsequent instruction is plus 4. So I know exactly the sequence of instructions to execute. What is problematic about branches? That when there is a branch, I no longer follow that sequential path. I need to jump somewhere else, right? How do I calculate this address that I jump to? I take the program counter, take the offset, add them together, and then jump, right? Which means the next instruction now has 2 possibilities. It's either the program counter plus 4 or the program counter plus the offset, if it's a branch instruction, right? And this is exactly what this circuitry is showing. You have an offset, and then simply because you are adding it to a program counter, which is 32-bit, you just do a sign extension. So just to do the proper add operation. And now you are adding the offset to the program counter. And then after I add them, what makes me jump? Like assume I got the, like going back to our example here. Assume I took the program counter and I added it to the offset. So now I have program counter plus the offset, which is the new address. Where should I store this new value? What register do I use to go to the memory to bring a new instruction? It's the program counter itself, right? So after you do this operation, you store it back to the program counter. And this is actually the branching itself, right? Updating the program counter is the act of branching, because program counter is the register used to take an address and bring an instruction. Okay. If we say next instruction is plus 4, so you say program counter is equal program counter plus 4. If you say your current instruction is a branch and you are jumping, your new program counter will be the old one plus the offset. Okay. So in this circuit, I'm taking really the addition operation and simply adding it back to the program counter. Here I have a question mark, because even if my current instruction is a branch, am I always jumping? If my current instruction is a branch, not a jump, not an absolute jump, but a branch, a conditional branch, BEQ or BNE, for example, in our example, does it mean that I will always jump? It's based on the condition, right? Because you have here a condition like this one here, for example, the example we're talking about. This is a BNE instruction. So you only jump if they are not equal. In our if example, if they are equal, I don't jump. I execute the subsequent instruction directly, right? So if you have a conditional branch, there are 2 possibilities. I either jump or I don't jump. Based on what? Based on your condition. If you have a BNE instruction like here, you take the 2 registers, compare them. If they are not equal, I jump. If they're equal, I don't jump. Right? It's quite simple. So this is why we have a question mark in our figure here. We say, well, in reality, I need the condition result. If the condition is true, I update the program counter. If the condition is not true, what do? I have to increase the program counter only by 4. Good. Please ask questions if that's not very clear to you. feel free to ask questions. Yeah. Yeah. Yeah.
That's the what's nested in it.
Yeah. I guess your question can be generalized to say if I have multiples of branches in a block, like if inside a 4 or if inside an F, and what would happen, right? So you are always relative, and this is a very good question. You're always relative to your current instruction, because the offset will be added to the current. I'm jumping or I'm branching from the current instruction I'm executing, right? And that's simply what you need to care about, the program counter of the current instruction. If there is an earlier branch or an after branch, I don't care about. Their rule will come when I execute their own branch. Make sense? It's as simple as your scope is not a for loop block. It's not a multiple nested if blocks. It's a single instruction, right? Well, that's a good point. You never go back for a branch, right? Or a jump. In case of a functional call, when you need to go back, that's a different story, because you need to store the condition somewhere. Like you need to store your current context somewhere, which is there is a register called the return address register, where you put the current address into before you jump. And when you come back, you load the return address to the program counter back. Any other questions? Okay. Okay, there are multiple other branch operations, but they just operate exactly on the same way. This one, for example, is say, less than. This is saying set if less than, right? So set if less than means you compare two registers, and then if S1, if S0 is less than S1, so the first operand is less than the second operand, then you set T0. Set T0 means make it 1. Otherwise, you make it 0, right? Good. This is basically used very commonly if you maintain a flag in your high-level code that you set to 1 or 0 based on a certain condition. The SLT operation can be used. And why we say this SLT operation is a branch, despite the fact that it's a set if less than. I'm not saying branch if less than. What do you think? Why we think of it as a branch instruction or a control flow instruction? What do you think? Yeah, because there is a condition there, and you execute two different type of operations depending on the result of the condition, right? And most likely the usage of SLT is also combined with an absolute branch afterwards, right? Because if you set that flag, you need to do something else, right? So it gives you a different result based on the condition of the branch, well, or the condition of that instruction. Yeah, there are similar branch less than or equal, branch greater or equal. There can be multiple type of branches, all behave just the same way. The only thing that change among these ones is how you calculate your condition. Okay. Now we go for the final instruction type, which is the jump type, which is the J format, where you have a 26-bit for address. This is different than branching in the sense that here you jump unconditional. You say, I want to jump to that address, right? It's not that you have to calculate a condition and then jump. No, this is an absolute jump, right? And simply this is the operand of the jump instruction, then 26-bit address. Again, how do I jump for a branch in a code? You add whatever value you have to your program counter, and you load it to the program counter. In case of a branch, it was an offset, so I add it. In case of a jump, it's an absolute address, so you just load it directly to the program counter. But now, this is only 26 bits, while my program counter is 32 bits. Again, what limitation this puts me on? In my code, I cannot really jump, an absolute jump, more than 26 bits away from my current address. So I don't have the full scope of the memory, right? That's a limitation. How do I really load that value to the program counter? you need to extend your 26 bits, right? So that's simply what you know. You basically, because you have your full memory, which is pointed to by the program counter, which is a 32-bit register. Now you are at a certain current instruction, so it has a certain program counter value. And then I have an absolute, this is basically the value, the program counter of the jump itself. And I'm saying I want to jump before or after that one with 26 bits, right? But I need to fill in, because the program counter is 32 bits, so I need to fill in the rest 6 bits. So I take the most significant, well, let's continue with that story. Forget about this 4 here. I continue with 6. I take the most significant 6 bits of my program counter to basically fill in the rest of the jump address. So I have 26 bits to the jump address. And then I have a rest of 6 bits because I'm jumping relative to the program counter. So I'm using these 6 bits from the program counter itself. Make sense? Because again, I'm just jumping relative to this. I'm only modifying the least significant 26 bits. The most significant 6 bits remain as is. Up until now, I guess it's intuitive, makes sense. But why we are saying here we don't need the full 6 bits, we only need 4. Where did I lose 2 bits? I usually make this question as a bonus question. It's an interesting one. So again, the question is, if you only have 26 bits to load as an absolute address, and you need to store this in your program counter, it's logical to say there are 6 bits that remain. You take the most significant 6 bits of the program counter. But here we're saying we take only 4. So I lost 2 somewhere, right? Yeah, Arjun? Not exactly, yeah. That's also not true. I like the way you're thinking, both of you. It's a good way to go to that, but that's not exactly the root cause. Yeah, there's a simpler reason than that. Yeah. Each address is 4 bytes. Your memory is byte addressable, so every address is in fact 1 byte. But what is the 4 bytes? Your instruction, right? So that's exactly the reason. Here, I'm not jumping anywhere in memory. I cannot jump in the middle of an instruction, right? So your step for jumping is in fact an instruction width, right? Which is 4 bytes. True? You cannot say, okay, I'm going to jump here, and this is, if there is an instruction here that has 4 bytes, I cannot jump in the middle of an instruction. Now I mess up my program. So no matter what is your jump, you must jump to an address that is the beginning of an instruction. And what is the instruction width? 4 bytes. How many bits you need for a 4-byte address? 2 bits, right? 2 bits for your address basically defines 4 bytes, because 2 to the power 2 is 4. This is why if you look here, there is 0, 0 at the beginning of how you massage your 26 bits to load them into a program counter, because you always jump in an instruction granularity, right? I jump by a step of 4 because I want to jump to a new instruction. Did you get that? Yeah. If you jump by 4, what happens? Sorry, can you repeat that question? So if there is 4 bits. Yeah, no, by using the 4 bits of the most significant 4 bits of the program counter. Yeah, but I'm left with 2. Yeah, but these 2 are the 0, 0 at the beginning. Right. So now 2 bits at the beginning, 0, 0 because of the granularity of the instruction, 4 bits for the most significant program counter. But if you look into the food, that's exactly what's happening here. There are 2 bits at the beginning, and the rest of the 4 bits of the 2 come from the program. Now you format them into 2 bits, and then you load them to the program. Makes sense? So I took the 26 bits, shifted by 2, because my granularity is 4 bytes, added 4 bits from the program counter, because I jumped it to the program counter, and then update the program counter. Okay? So one final note, and maybe you can have a break for 5 minutes. Compare this to the branch. Okay? If I compare this to the branch, in the branch I had a condition, whether this question mark thing, whether I should really update the approval counter or not. But here I don't have this question mark. Why that's the case? So this is an absolute jump, unconditional branching. Good. So you always going to jump to this address. In a conditional branch, you need first to determine your condition, and based on the condition, you determine whether you should jump or not. Good. That's why it goes directly to the program count. Okay. If there are no questions, maybe you can have a 7-minute break and then we start at 1:35. Yeah, you can come in. I guess we should start. We have one question, which is when we talked about branches, if you have an immediate value of an object that you want to jump to, right? Which means you are limited to jumping from the current instruction or after by simply to the power 15 minus 1, right? Because it's a sign offset. What if I want to branch more than that? What can I do? Given what we discussed up until the moment, do you see a way where in fact I can enable branching? Like assume, for example, someone wrote a program, and there is a for loop or an if condition that is very large to the level that we need to jump more than really 16 bits. How can I do it in a assembly? Now you are a compiler having this high level C code that mandates you to jump conditionally, like with a branch, jump more than 16 bits. What can you do? Is there something we can do given what we learned so far about the maps instruction set? Yep. Jump twice can definitely be a possibility, but how to do it? Like you write two jump instructions. Put in mind this is a conditional branch, right? This is conditional branch. You only need to jump to that location if the branch is true, like the condition is true. You are in the right direction, so you need to basically do more than one operation. Yeah.
You branch to something closer and you do a jump operation to get to the box.
So you jump twice, but the second one has to be an absolute jump, right? Because why it has to be an absolute jump? Because you already branched it in the first one. So what you would do. Am I going back in that direction or I'm going? Yeah. So what you can do here is, okay. Now assume I want to execute this issue, but my L1 is larger than the 16-bit offset. But I need two instructions here. I say, well, I use a branch, conditional branch, and a jump. And this is in fact one way of doing it. And your answer is also another way of putting the down the non-branching, then you can do the branching side to do the same thing. Anyway, but here I'm putting the branch, putting the absolute jump to L1. First of all, why the jump to L1 works, why the branch does not. Why if the L1 is a very large value, this one is not a value, this one is a value. Yeah. The idea?
Is more jump has the longer address.
So this is one for this is 16, right? What we discuss. This is asking this question to see how does the ISA dictates really not only what the hardware will be able to do, but this is a rule of who is going to do that for us. That's the compiler, right? The compiler is the one that is going to see that if condition or for loop or whatever it is, and decide, well, your ops larger than what the hardware can support, then I need to break it down to two instructions, right? The one that's creating this assembly is the compiler. And who governs the compiler is really the ISA, right? So the limitations in ISA impacts both the software and the hardware. Good. You see me like emphasizing the same concept again and again because there are a few concepts in architecture that we keep appearing everywhere. And if you understand them well, you are able to really make good judgments about good architecture. So what we do now is we flip the branch type from BAQ to BNE because I want to go to L1 if the condition is equal. So I say if they are not equal, don't execute the jump, just continue normally. If they are equal, which is our original branch, I need to jump to L1. So I use an absolute jump or non-conditional jump to L1. Makes sense? Yeah.
So it says this spreadsheet for pay. Let's not go away from the current address, it's not from address 0, right?
Before the absolute job.
Yeah, like in general, L1 is just too large for 16 bits.
Yeah, but so large for even from the current address, right? Because again, put in mind that we use this offset in a branch. Why do that open count? So we are always branching from the current open count to the see that?
Yeah, it's not, that's not.
That's all. Okay, so now, given that we talk about jumps, we want to use them. So we saw examples of branch and conditions like if statements and for loops. What about functional code? So in functional code, there is one thing special that I was discussing with Steven when we asked the question. In those functional codes, they are different than if statements and for loops in the sense that I need to come back to the location I jumped from, right? So if you have a function in C, and then inside this function of C, you call another function. This function you will have to jump to F2. But after you are done, what do? You have to go back to the exact same location that you called F2 from, right? Again, we discussed in Twist. So there is an extra step you do here that B&E or conditional branches and absolute jumps don't have, which is I need to return to the address that I'm from, right? So there is another instruction that is called simply jump and link, JAL, jump and link, right? And the idea is I jump, but before I jump, I store the current program counter somewhere, such that when I'm done, I return to that program counter value, right? This somewhere is usually referred to as the link register or the return address register. Good. Some instruction sets call it link register. This is very common in ARM. And I guess the best is calling it the return address RTL. Right? But it's just a convention of the name. Right? Good. So this is the jump and link. You have the procedure address. It's 1026 bits. You have the opcode. Then when you finish, so now I'm using JAL to do that jump. Once I'm at the return point, well, I need to go back there, right? How do I do it? Well, with another jump, right? So you use a function called an instruction called jump return, and you load the return address into it, right? So this is basically the GR function, the GR operation here with the GR instruction. Okay. You see what I mean? So if I want to jump to a function call, I use the jump and link instruction. This one will store. It will by default, so you don't have to store it yourself. Jump and link means store the current program counter to the return address. So RA, after this instruction, will have the current program counter value. In reality, just to be, well, maybe I will leave this to last and ask you this as a question, but RA will be the program counter. And then after I'm done with all the code here and I want to return, I basically call GR, and my address that I'm going to jump to is simply my the value that is stored in RA. How GR is different than the normal jump we had, the absolute one? That the normal jump we discussed so far takes an immediate value, 24-bit. The jump return takes a register value, right? Which is the 32-bit that's going to be stored to the program counter. Good? Now, I will ask a question and then take your question. I guess you're raising your hand, right? So I will ask a question and then take your question. Here I'm saying something a little bit not very correct, and you should really know the answer for it. When I'm returning, am I really returning to the program counter value? So if I jump from this point, and this point has the address program counter, do you really return to the program counter? Or where do you return? Yeah. Or before it? Or after it, right? Because you basically execute the subsequent instruction. If I call that instruction call, think about your C code. You come back to the one after, the line after it, right? The line after it is stored in program counter +4. Good. So what you store really here is the program counter +4, but yeah, please. Yeah, great. So for the reason that I was mentioning, that the regular jump, if you look into its definition here, it has the opcode and 26-bit immediate value, right? It cannot accept a register. You see what I mean? But your program counter value is stored in the return address register. So you need another type of instruction that accepts the register as an operand, right, to the instruction. This is why, in fact, the GR, despite being a jump instruction, you see that it's of an R format, not a J format, right? It's an R format because it takes a register as a source operand. Good. Other questions? Okay. Now, some more discussions about procedure calls. Like, for example, well, what if I need more registers than what I can afford? We only have 32 registers. What if I need more registers? Well, you start using memory. You use the stack basic, right? And this is also something you have learned about in 2sh and 2si, right? If I jump, well, you push in the registers into the stack, you execute your new procedure or function, and once you're done, you load the stack back, right? This is called context switch. Right? And for the stack, we're using the stack pointer, and there are two special instructions for the stack pointer. There's a push and the pop of the stack pointer. Okay, good. So now we go back to the immediate. It's not that we go back. In fact, we didn't discuss the immediate instructions yet. If you think what we discussed so far is the R-type instructions, which are the arithmetic, and then load store, which are the memory, and then jump and branches. And then we talked about the usages of jump and branches. There are other type jumps that go back to the R-type. We still need to discuss the immediate type of instructions, right? The ones that would have an immediate value inside their opcode, right? And we need to think of why we come up with such a decision. If we're designing our own ISA, why would I put immediate values as part of the opcode of the instruction itself? Why, for example, not put it in a register and use that, right? Which I guess someone has suggested at the beginning of the stage. Assume, for example, you want to do something like x equal x plus 3, the thing that we discussed at the beginning. And this one is going to translate into add, either can be translated into add R1, R2, R1, R1, and 3. Or if you don't have an immediate value instruction, this is going to be translated into first move R1, you move 3 into it, and then you add, this has to be R2, and then you add R1, R1, and R2, right? And this move can be as simple as you simply even can store this in the memory if you have a move instruction and then load it from the memory. So it can be even translated into further type of instructions. You see what I'm saying? So what we have on the this is going to be right side. What we have here is if I'm supporting immediate value arithmetic instructions, which is what currently MIPS is doing, versus if I didn't have such support, I cannot do arithmetic operations with immediate values. Right? How do I do it? You load it first to a register for a move operation, for example, which C6 is supporting as an instance, and then use this new register to basically handle it. Now the question is, and this is why I want you to think about the philosophy. Why do I dedicate a certain type for immediate value instructions? It has to go back to performance, right? If you look into analyzing code applications, it's very common that you operate in immediate values. If you have counters, if you have loops that increase the counter, most of the time you are adding variables to immediate values, right? You are reading some values from the screen and they turn out to be immediate. So operating on immediate values, and usually small immediate values, is very common in code base. Now, if this is the common case, I want to make it fast. Make the common case fast, right? How do I make it fast? If you embed the immediate value in the instruction that is doing the operation itself, that means you execute it in a single instruction. On the other hand, if you don't do this, and you load it first, and then do your usual arithmetic instruction that we discussed until now, then you execute it into instructions. So now you reduce your number of instructions by half from 2 to 1. Sometimes you don't have a move, it's even from 3 to 1. That means you make your execution fast. Does it worth it? Again, it go back to your analysis of your application. This is very common to happen. Then yes, it's really worth it, right? To design the ISA like this. And most modern ISAs have an embedded support for immediate values. Why? Again, because most common applications operate a lot on immediate values, right? So you want to make them fast. Okay. Okay, what is the format of these instructions? Again, we dedicate 16 bits for the immediate value. And because we say these are usually small constants, 16 bits most of the time are sufficient. We will discuss in a few minutes what if they are larger than 16 bits. But for now, this is your immediate value. This is your source. So if you are adding R1 to 3, this will be your 3, included directly inside the instruction itself. RS is your R1, and your destination is also R1. Can be something else. Happens to be the same register. Good. And this opcode is determining that this is an add to an immediate value. Usually in RISC instructions, this is called in RISC instruction sets, it's called add-I, add immediate value, right? Yeah, true. And we will discuss in a second what if my application has a larger. So we'll follow the same philosophy of the jump. Yeah, okay, that's exactly the slide that I guess answers your question. What if I have constants or immediate values that are larger than 16 bits? What do I do? Well, simply you use the upper and lower of a register, right? So you say, I want to load an upper immediate to a register and then a lower immediate to a register and then do an OR operation. So what you do here is this is basically called load upper immediate. Still has a 16 bit, which is the limit of the ISA, but it takes this and load it to the most significant, the upper half of the register, right? Now I want to go and load the lower half. What do? You just do a simple OR operation with the lower 16-bit half, which means at the end of the day, the T's here will end up with 32 bits of that immediate value, right? Now, in this example, we did the thing that we went against in the previous slide, right? If you go back to the previous slide, if you go back here, we said, well, it's a common case. I want to make it one instruction, but I ended up in the larger than 16-bit to make it 2 instructions. Why that's the case? Because what they found that the common case is this is for small constants. Most of the time, applications operate in small constants that are less than 16 bits. So it's good to accelerate those. It's less likely that you operate in constant values that are very large. And this is why it doesn't worth really adding instructions to support them. In addition to the fact that it's going to be quite hard because you need to accommodate what 32-bit, but my instructions are only 32 bits. So I cannot really do it physically, right? So it's okay really not to do it for large values. They appear less. I don't want to really accelerate it. It's okay to suffer 2 instructions. Good. Questions? Good. So far what we have is we discussed types of instructions, and we took in fact 1 instruction of every type. And we had a sense of how the ISA is encoding them and how we can execute them in hardware, right? Like an add, a jump, a branch, the conditional branch, the jump for the procedure, and the immediate value instructions. So we are ready to think of how we can implement them now, right? So in the process, whether it's implementing those, we have the register file that we discussed already. The IC is supporting 32 registers in the register file. We also discussed the circuitry where we update the program counter with the branch offset, where the program counter can be simply added to the branch offset through an add operation, produce the new branch conditional, or if you're not branching, like the sequential execution, or if the branch condition is false, I'm adding program counter to 4 to calculate the address of the new instruction, right? So this is a circuitry that you would need to calculate your next instruction to execute. Either your program counter plus 4 or the program counter plus the branch offset. In reality, is that true? Or am I missing something? Is there a third possibility? Yeah, the jumping one that we already discussed that. In fact, loading the program counter with an absolute jump address value. Thank you. Right. So this circuit basically is not really discussing this at the moment. Right. We will come into it later. Right? Like we will expand that circuit when we talk about the full thing to support the junction. And then we have an ALU that we operated on, and then we have a memory that basically dealt with using the load store operations, right? In that memory, it's byte addressable, and simply means every single address is pointing to one byte. Instructions are stored in that memory in a word format, 4 bytes each, which means in reality the first 2 bits of the program counter are always incremented by 4, so we don't care about them. And we discussed whether it should be big endian, little endian based on what type you read first. That's an orthogonal topic. You go to the memory with an address. In case of an instruction, you go to the memory with the program counter, and then you read your instruction. In case of a load operation, you go to the memory with an address, and you read data from the memory to write to a register. In case of a store, you go to the memory with an address, and with the data that you read from a register, then you write to the memory. Good. So this is summarizing more or less all the instruction types we have discussed so far. They are being now discrete. Everyone is on its own. They're not put together. But our goal throughout this course is really to put them together in a real architecture and then optimize that architecture along the way, right? So we'll start with a sequential processor that puts the full circuitry together, see how the control path works, the data path works in a single cycle processor. This is very inefficient. No one in the world is implementing it, but it's important to go through it to understand. And then we pipeline it, and then we have it multi-core, then we have it out for the processor, superscalar, we add caches, and all the interesting stuff. Okay. Is that clear enough how the big picture really plays together? Okay. So yeah, this summaries we already went through. Yeah, that's also another summary of the types of the instructions. They already also discussed. Yeah, going back again to the philosophy of MEPS, which is the processor that we are building. The risk mindset from the beginning is you want to simplify your hardware as much as you can. Why I want to simplify it? To make it scalable and fast, right? The simpler you are, the more regular you are, which means you can scale easily, and the faster you can execute things without a lot of complex logic, right? During the break, one of you were discussing with me what would happen in a CISC x86 branch condition. I have variable instruction length. How do I jump to? Well, I have variable immediate values. How do I add? It's a very complex logic to determine how do you resolve branches in x86, right? So why in RISC, it's very simple because everything is fixed, limited. There is no variability or uncertainty in your math. Yeah, well again that signed representation, 2's complex representation is something again I assume you know by your 4th year from the 2DI. How do you represent a negative number, right? Either sign and mantissa or 2's complement, right? 1's complement, all the representation things you have had. Yeah, this is something that will come into us when circuitry. We already have seen in the offset of the branch. If you have a small number that you want to add to a larger number, like our offset was 16-bit, and I'm adding it to a 32-bit program counter. But your adder is regular, it's 32 by 32. So how do you extend the 16-bit to be 32? There is either to, like you do the 0 extending, so your most significant bits are zeros, or you do the sign extending. When do I do sign extending? When do I do 0 extending? Do you know even what is extend? This is a digital design kind of discussion, right? So you do the sign extension if your offset is signed, because in reality, if it was signed, it means that the most significant bit is the sign. So if it's 1, it means it's negative. Now, if I 0 extend it, I mistakenly transform the number from negative to positive. Right? So I cannot really 0 extend the sign number. What we do is we do sign extension. You take the last bit and replicate it, right? If it's a 1, it's a 1. If it's a 0, it's a 0. It's called sign extension of a number, right? And we need to sign extend our offset before adding it to the program counter. Okay? Now, about designing those discrete components, the ALU, which is going to do the most of the arithmetic operation. In 2DI, I would assume you design the full adder, maybe a 32-bit adder or an 8-bit adder. Is that true? At the very least, you must have, like a full adder, and you cascade it to design like a multi-bit adder, right? And then basically how the adder can work as a subtractor as well, right? In a modern ALU, it's basically assumed to have all the arithmetic operations, an adder, multiplier, subtractor, and this and the ALU is reading for overheads and reducing to a result. Everything is 32-bit in the MEMS machine. And there are some flags that you have. Like there's an overflow flag, there's a 0 flag. And then you basically here, because you perform different types of operations, you can do an add, multiply, or subtract. You need some bits to determine what operation then you need to do. So I'm assuming that these selection lines of the operation are 4 bits. How many operations I can conduct? 16 different operations in the ALU, right? A question to you from our previous lecture: who is going to drive these guys? Who is going to tell the ALU the value of these 4 bits to conduct the operation? The control unit, right? We said there is a control path. Its rule is to fetch the instruction, understand it, and feed the bits to the execution unit with the right selection lines. Good. Yeah, two's complement I'm not going to review. You guys are great. And then full adder. This is again another review from 2DI. And then how do you put full adders together to perform a 32-bit ripple carry adder? That's a very low level, again, digital design discussion. We don't need much in the course, but also I would assume you already know. I'm just putting it here for full disclosure. These are things that, well, if you don't know, just go ahead and read. Now, one important thing to know is in the ALU, if I'm adding 32-bit numbers together, what is the width of the result? If you are adding 8-bit by 8-bit, what is the output width? 8-bit, that's one answer. Yeah. 9 bits, right? Think about it. For the 8-bit example, even with, let's take less number of bits, 3 bits by 3 bits. What is the maximum representation of a 3-bit? What is the maximum value? 7. If you talk about, ignore the sign for now, so 7 bits. Sorry, a value of 7. 7 plus 7 is what? 14. How many bits you need to represent 14? 4, right? So there is always one extra bit, because if you are adding 2 numbers of a certain width, the result is basically can be the double of each, right? So if you're adding 32-bit to a 32-bit, your result maximum needs 33 bits. But our ALU, in fact, would have only 32-bit as an output. Why? I would have 32-bit only as an output. So where this result is going to be written at the end? In the register file. After I add, I'm going to take the result and write it to the register file. The width of the register is 32-bit. I cannot have more than 32-bit as an output from the ALU going to the register file. What is the bit? The 33 bits that I'm going to use is the overflow. This is the meaning of an overflow. Basically, it means your output is larger than what you can accommodate in your width. Right? How do I determine the overflow? In case of an addition is very simple. You take the 33 bit, like the last bit of your output, and this is the overflow. Right? So here we have an example of adding 7 to 3. And the result is, well, 7 to 3 gives you, if we're talking about a signed number, yeah, this discusses how you determine overflow in case of a signed thing. So you have to take really the sign and the bit. And it is okay, carry into the most significant, XOR with the carry out to the most significant, it's going to be your overflow. So that's the key basically, is you take this one and this one, you XOR, gives you overflow. Why that's the case? Think about it, and by next week we can discuss. But this is something very easily you can determine your own. Start with 4 bits and see what do you get, right? For example, here, first of all, in an addition, and maybe this thing we conclude with. In an addition, if you add 2 signed numbers and both have the same sign, what will be the sign of the output? If you are adding 2 positive numbers, the result is, if you are adding 2 negative numbers, the result is negative. Now, how do I know that an overflow happened? The output of the result is different than what you expect from the output. So if you have 2 negative numbers, like -4, -5, and you end up with a 7, well, an overflow has happened, right? If you are adding 2 positive numbers, 7 and 3, but you end up with -6, then an overflow has happened. Make sense? Good. How do I know that the output has changed the sign? Well, the sign is your last bit, your most significant bit, right? This is why you are using the carry to the most significant bit, the carry out of the most significant bit, and XOR them together. Good. Try to figure this out in your own. If you follow a few examples, you'll be able to figure it out. I promise that this will be the last thing, but I think we are approaching. We're not approaching the end. Okay. Yeah, well, okay. So the rest of the slides are in fact less relevant because it just says what do I need to support additionally in the ALU, which is like at the digital design level. But it's okay. We can stop here and we can continue from that discussion next week. Thanks.